All right, so today we're going to move on to more of case studies looking at carbonate shoals, ridges, grooves, and canyons and how they look in seismic data. So, as you may or may not know, carbonate shoals, ridges, and grooves are pretty critical elements in understanding the ancient depositional environments and modern carbonate platforms. So they have very distinctive signatures and seismic reflection data that help us map these ancient shorelines and platform margins and also provide insights into paleocurrent patterns, sea level changes, and potential hydrocarbon reservoirs. And their ability to accurately, the ability to accurately identify and interpret features in seismic data is pretty fundamental, whether you're looking at it for academic purposes or for petroleum exploration. And so here we've got a lovely picture of a place I wouldn't mind being right now, but the carbonate sands of Andros Island in the Bahamas, which is one of the more commonly used modern analogs for carbonate sand shores. So let's go into our first case study. We'll look at mapping cliniforms and angular unconformities in prograding reef systems. And so here we've got an example of a system in the Middle East where we have seismic reflectivity cross-sections shown before and after structurally oriented filtering, okay? And so notice that I'm filtering the data, or we're filtering the data in this case, and that's because having the cleanest data you possibly can will help you with your interpretation. And so structurally oriented filtering is a very common step that most software packages have, and you can apply it after seismic processing. So you as an interpreter should be able to apply this step. And so you can notice, particularly in that black square, where you've got an improvement in resolution and reflection termination continuity. Okay, now looking back at this data, we can see that the system is a buildup that's kind of coalesced through time and filling up the space as it builds up and builds out just a little bit. We've also got some seismic sections. You can zoom in. We're zooming in right here, where you can map out individual mounds. And so one technique you may want to use is using the wiggle traces or variable wiggle displays like this as you're looking for very fine scale changes. And so employing in your seismic program, the wiggle trace to be shown can help you with your interpretation. Here's an example, again, same area, looking at some time slices where we've got what the edge of the platform looks like before structurally oriented filtering and then after. And here we're looking at it with a co-render of dip and azimuth from the flattened volumes. And we use the flattened volumes to account for compaction that may happen. So quick case study there. Now we're going to look at some shoals, and I'll show you some examples of using coherence, sweetness, and spectral decomposition. So here's a vertical seismic section through the seismic data. This is in the Permian Basin of West Texas, so some onshore data. You can see mapped out the top of the ABO platform, and then also a notation here about where the base of the platform is. So what we're looking at is kind of lying in here between those two black arrows. When we look at this with horizon slices through coherence on the left and then the 40 Hertz spectral magnitude volume along the ABO horizon, you can see the kind of some of the faults you can see in the spectral magnitude, the edge of the shelf, as well as the location of some shoals in the area, kind of marked by these turquoise arrows. These shoals are kind of related in this case study a little bit to production. I have in my notes that it was a little bit unpredictable, but they do think there's some relationship here. You can see they've got a lot of well logs there, or wells that have been drilled as analogs. And then here's another example of shoals, this time in the Campos Basin offshore Brazil, where we're showing the platform area in sweetness with spectral elements and then how they're interpreting it. And so you can notice that they've done a really good job picking out some of the different elements of the carbonate system from the reef crest kind of marked here. And you could see that in this case right here with the spectral components. It also shows up really well with sweetness, which is an attribute that's derived from amplitude and frequency. The shoal is marked here as S4 in these figures, and there is another one marked as S3, but they have different lithologies. Shoal 4 is a packstone, Shoal 3 is a grainstone. And so you can see that Shoal 3, the grainstone, appears much brighter, higher sweetness than does Shoal 4, and that's probably because of a variation in the lithologies. All right, let's look at a couple examples of some spurs and grooves, this time using dip azimuth, dip magnitude, and coherence. And so in this case, we've got some modern analogs here in French Polynesia, here in the Bahama Islands, and then here in the Heron Islands of Australia. And so looking at these modern analogs is really important because we can see here what the features should look like in seismic data. And so we're going to look for these patterns now in seismic. So here is a case study that was done a while back with a co-rendering of dip azimuth, dip magnitude, and coherence. And so what I'm going to do is I'm going to move up in time so we can see the system. So we're starting here at a time of 700 milliseconds. You can see the coherence is in the kind of grayscale as usual. We've got amplitude shown on the vertical slice. And then dip azimuth, the directions are related to this kind of northeast, southwest color scale, where if they're dipping to the north, they're bluer, south, they're more yellow. All right, so let's move up. All right, so we can see here some dipping to the north in a few cases. Dipping to the west, northwest. So remember, there was a lot of variation in those features that I just showed you. All right, we can notice in the seismic amplitude data a bit of pinch out to the south. So we're kind of thinking our way through this problem here, as well as a pinch out to the east. And then a pinch out to the southeast. And so we're able to see that now that I've displayed the dip azimuth on there a little bit more. All right, moving that time slice up a little bit further, and then further still. Now we're going to move back down through it. And so you can see how looking at this feature, when we can use the azimuth to help us understand the three-dimensional structure. So there we've got pinch out to the north, to the north, to the north, and then to the south, and the south. And so this is kind of an interesting geometry if you're a geologist, just to kind of pay attention to. And so hopefully you could see how you could use dip azimuth to help you map out some of the geometry of exactly what's going on for these very finer scale features that are hard to see. All right, a couple examples of canyons on a carbonate bank. So here we're in the Carnarvon Basin in Northwest Australia, and we've got a vertical slice through the seismic amplitude that's been co-rendered with the most negative structural curvature. And so what this co-rendering does is it really highlights some of those incised canyons within that carbonate bank. And so you can see here the blue colors really showing the incision of the canyons. And you could see the canyons fine in seismic amplitude, but it really accentuates the features. And in this case, the curvature was calculated on a very long wavelength of about 1 kilometer. So it also gives you a sense of the size of these canyons. Zooming into them, you could see it in a little bit more detail here, where the canyons are in the seismic amplitude, but then also highlighted by the seismic curvature. And then one of the things you could do if you wanted to do this for your mapping or reservoir characterization is you can set your most negative curvature features. In this case, we're setting them to a red color so that we can extract them as geobodies. And so here's kind of an example of what those canyons look like once they've been extracted as geobodies in the software. All right, so that wraps up this quick kind of example of shoals, ridges, grooves, and canyons. Just as a summary, since I only went through a few examples, some of the things you want to look for in carbonate shoals are mounded seismic facies. You'll expect high amplitude responses, kind of those linear or curvilinear patterns. You may be able to see, depending on the resolution of your seismic, internal cross-bedding, and those shoals can be stacked complexes, so keep that in mind. With ridges, they tend to have a linear positive relief feature. They align with paleo currents. You could see the internal progradational patterns and kind of a sharp amplitude contrast within them. Grooves tend to have that negative kind of linear relief pattern. They could have channel-like geometries. Usually you could see the erosional surfaces. Again, depends on your seismic quality. With canyons, they're deeply incised, like in that last example I showed you. They kind of have that V-shaped cross pattern or cross section. We highlighted them in curvature as I showed in that example. And so some of the key attributes for looking at these types of features would be RMS amplitude for lithology, using coherence or edge detection. Dip and azimuth can be really great for structural trends. Seeing the direction that the platform or the shoals or, many of these features are, relatively, can be relatively smaller scale. You can see that the mounding of them or the carving of them. Spectral decomposition can be really great for architecture too. And then if you have a curvedness or curvature attribute, that can be great for morphology and, seeing those geometric patterns. So as always, thanks for listening.